Hey there. So this lesson, we are looking at resonance in air columns. Basically, we're going to hear the patterns that are possible. So you're used to seeing standing waves and nodes and antinodes with physical waves where you can see the springs vibrating back and forth. Of course, with sound waves, you can't see it. And so we are going to instead be hearing it. And I'll be describing what we're hearing and what that means visually as well. So here we go. We're looking at resonance in air columns. We're really looking at standing waves and sound. And you saw a video in the previous lesson where the person had two speakers facing each other, and then the microphone went along and found quiet spots and loud spots. So instead, what we're going to be doing is we're going to be listening at the top of an air column. So this is often called a closed air column. It can't be closed at both ends, obviously, or else no energy would get in there of the sound wave. So it's open at one end, closed at the other, often called. So where in my apparatus, I'll show it's water at the end. So it's an air column, and then it becomes water. So it's not an air column anymore, of course. So that's considered a closed end because water is heavier, more dense, and so on than air. And so the top is an open hole, and it's an open end like a free end, and the bottom is closed. So it's like a fixed end. And so it should be pretty obvious whether you have a node or an antinode in a pattern. So when I was sending the springs back and forth, if you had a spot that was fixed and you had a pattern like with the drill demonstration, the bungee cord, it was like nodes at the end because they were fixed, and then antinodes would be where it's not fixed. And so hopefully it makes sense that you're going to have an antinode at the top where it's open and a node at the bottom where it's fixed. So what that means then, if we think about the shortest pattern that's possible here, we have to have an open end antinode and a node. And so if we look at that, we have like an open end and a node. And so that's the smallest fraction of a wavelength possible. So it'd be something like this if we show it visually using the regular kind of sine wave patterns. Okay, so if you're looking at the full wavelength going from there to there, right, that's a full wavelength, and you can tell that that would be 1/4. Or maybe I should use green. Excuse me. I'll use red for this. So this is 1/4 of a wavelength. Okay, and that's just what fits in there. So it's 1/4, of course. And so the pattern, just have all spots filled in on the thing here. This is 1/4 of a wavelength. Hopefully that makes sense as to why. So that's what we know is kind of going on. And so if we have a standing wave, you'll know because it'll actually get louder because of resonance. So the sound source is this vibration, and it sends out sound in the air, but it's not super loud. It's not a ton of energy all at once. So this air column would set up a standing wave. The first length that'll lead to standing wave, which you'll hear is an increase in the volume, would be again 1/4 of a wavelength. And so this water level here, you can actually adjust by moving this canister up and down. And so it has a tube connected to the bottom, and it allows the water level will always be equal. So I can't see in this picture where the water level is, if there's water in it or not. But if the water level in the canister was here, then the water level would even out over time to be the same there. It's Archimedes' principle, it's fluid dynamics, and so on. There's construction workers that are old school and have like networks of tubes with a dyed water, like a colored water, and they put the tubes all around, and basically you can adjust the deck blocks or the posts for the deck to all have the same height based on the water level, rather than using like lasers, which tend to be a little harder to see during the day. So this is the apparatus that I have. I'll just show you a little bit here. Volume's up nice and loud here. Orange shirt day here at Rito. So I'm just showing you there that the sound is that's my microphone there. And so when the tuning fork's really near the microphone, you can hear it really well. And then what we're going to hear is we're going to hear amplification. So right now I think the water level's around there. We'll see it go up and down. So it's actually at the shortest length where resonance happens right away. You'll see me. see how it's getting louder when the tuning fork is over the air column. That's because you've got a quarter of a wavelength in there, so you're getting a standing wave. Okay, and we'll come back to this video in a bit because there's more to it than just the first resonant length, but let's do some work with that first. So you can get the wavelength because you can measure the actual length, and then you can actually get the speed because we know V equals F lambda, right? So if we look at a known frequency here, let's go through the given information first. And so we have a frequency of 256 hertz. That was given. We have the first resonant length. So it's the shortest resonant length. That's important because or else you'd be off by factors of multiples anyways of what it of what the frequency would be. So we'd have 1/4 wavelength. Just list what you know. 1/4 wavelength is the shortest resonant length. That's 31.5 centimeters. Or in other words, that is 0.315 meters. And it's asking for, in part A, the speed. So in A, what's the speed equal to? Okay, so maybe I'll move this over here and have room to do ABC across the board here. So based on all of that information, this information and this information, let's see, V equals F lambda. That's your, so you're given here, and then your required was here, and then now your analyze is there. And let's keep going. So let's put numbers in. So we have V equals F lambda. The F is the frequency, 256, and the wavelength. We need to do a little bit of work first in order to plug into there. Okay, so basically from this starting thing here, I'll write the 1/4 in as well so I can be clear. But we just, I think I showed this earlier in the course at some point. We just multiply both sides by 4, and that's gone. And we get wavelength equals whatever 4 times 0.315 is. So 4 times 0.315 gives you 1.26. Okay, so we've got a wavelength of 1.26 meters. So we can put that number in. Now we have that 1.26 times 256. 322.56. Now that's what we're getting as just raw numbers. We're looking at what we started with. We started with 3 significant digits in each. So we have 3 significant digits, 3 significant digits. Digs, or however you want to write it. And so, yeah, we're multiplying here. So you'd want to keep the same number of significant digits. And so we're going to round based on that 5. And so we keep it even based on the actual, or the better rule. 322 meters per second is what you can actually be confident of. That 6 is, the 5 and the 6 are a little too much uncertainty in those ones. So let's just move that down and over. I'm going to move things around here a little bit to make room for this on the page. There we go. So there's A, and then in B, oh, actually, just recognized it. This was A up here, wasn't it? Not as much room as I thought. A is really this stuff. This is really B. So maybe I'll just move that back because it looks like I'll have tons of room. Regret it, you never know. So this is B. And then in C, if we're doing a little review of this, let's move this up a little bit more here. So room for C sort of in line here. If we did a little review of this, you'd have your 331 plus 0.59 T equation to do with the temperature information. So let's remind ourselves here, we have given information here of, so we have the speed of sound. So V equals 322. Now this is where, if you're doing calculations and trying to get the best approximation of the temperature possible, it would make sense to continue with decimals, and then you'd claim how confident you are of the temperature to the 3 significant digits. And so you have this, and then that's where you'd say, okay, well, our equation that we know from this, wow, a little glitch there with the computer. Then it thought I was trying to throw it. Yeah, we have the equation, and we just plug numbers in and solve, right? So we have the 322.56 equals the 331 plus 0.59t. And so we just solve mathematically. We're just going to subtract 331 from both sides. And again, to those of you that had feedback about equations, start with the original and then plug in the 322 and just show your steps. It's a nice systematic way of going about it. So 0.59t equals whatever that result ends up being. And so we're going to do 322.56, subtract the 331, giving us negative 0.8.44. And then dividing both sides by 0.59. I guess it wasn't a water apparatus that was adjusting the air column. If this was the case, it'd be freezing. Dividing by 0.59 gives us minus 14.3. You'd be freezing your fingers off, and the water would start to freeze. But it doesn't matter. Okay, so just that's what the temperature would be if this was what their values were. So 14.3 to 3 significant digits. Now I could show that it was 0.5 ... And then of course we choose to keep 3 significant digits. I'll just do SDs for short. Right here. So our final answer here, temperature, we'd say, okay, well, we're pretty confident that the temperature was approximately 14.3 degrees Celsius, the 0.3 being an estimated value based on the 6 from 256 and the 5 from 31.5 being estimated values. That's how the numbers combined. So obviously along the way here, I like that people are doing therefore statements. I'll encourage you to keep doing that. That's your paraphrase part of the process and so on. Okay, so this was part C here. So A, B, and C all worked out. Hopefully that makes sense and easy to follow. The rest of the story, I'll play the video after I go through this, but we have this first resonant length of 1/4. And so you can picture the next length that would set up resonance, right? We have to just keep, right now there wouldn't be resonance if this is the bottom of the air column, right? Because you can't fit a nice multiple of a fraction or of the quarter wavelength or whatever, multiple of a quarter wavelength in there. Finally, when I come down to this length right here, that's when you'd have, quarters fitting in there and even multiples, and also matching the idea of there being a node at this end and an antinode at that end, right? So you'd have to extend all the way down to that. And so it's pretty easy to do the math here, where if this was 10 centimeters, then you'd be expecting, the next resonant length to happen around 30 centimeters. So when I'm doing this lab, one of the things I do, at least part of the video, I think the first part it was a little slower, but if you found it was like 15 centimeters here, you'd be like multiply it by 3, and around here you're going to listen for resonance. You don't want to just use the times 3 number, because any error in that short one gets multiplied by a factor of 3, and you have 3 times as much error. But you can at least use it as a quick way to get in the ballpark, and then continue that process further, and you'll have 1, 2, 3, 4, 5 quarters, right, all the way down. So that would be 50 centimeters if the original one was 10, and so on. Okay, so pretty understandable pattern there. So just to be clear here, only these specific lengths cause resonance, right? It's a nice predictable pattern. Yeah, those are your natural frequencies, if you will, for those air column lengths. So if the second resonant length was 90, you'd be able to work backwards, right? You'd say, okay, well, 3/4 wavelength equals 90, and then you just solve and you'd be able to get the number. Okay, so this is the kind of prediction and predictability and understanding that we need to have to do with air column resonance. So that's a closed at one end or a closed air column. Sometimes textbooks or websites might call it. Another one is an open air column or an open at both ends air column. And so open at both ends has to have an antinode at both ends. And so this is the only pattern that can fit in. If you look at what that is, it's 2/4, which is 1/2. Okay, so that's a half a wavelength. And then extend that pattern again, and then you're going to have, a half down at the bottom, finally again. And so these ones are always a little bit longer. Okay, so it's harder to do this experimentally because the tubes have to be longer than the closed end. So the apparatus I typically use is closed at one end, and it's a little more manageable because your first resonant length might be around 23 centimeters or something, rather than almost half a meter, 43 centimeters. Okay, so if the first resonant length was 43 centimeters, you would just multiply both sides by 2 and get the wavelength is 86 centimeters. And it's an important calculation to be able to do with the work we're doing. So a link to musical instruments is pretty obvious. You're going to see air columns in all sorts of instruments. Sometimes the air column is just for amplification. Sometimes it's for determining the frequency that actually is produced. So in a recorder, there's lots of frequencies here based on the whistle that's here. It produces all sorts of frequencies. And then the one that gets amplified is determined by the length you choose, right? Because different lengths are going to have different wavelengths that fit in there as a quarter of a wavelength. And so that's going to pick up a different frequency from the bunch and amplify it. Okay? And so plugging the holes lengthens the air column, obviously. And so the purpose is that you determine which frequency is going to get amplified, but really amplifying the sound is a big part of it as well. So picking the frequency in this type of instrument and amplifying it. Some instruments, like an acoustic guitar, for example, isn't picking the frequency that comes from the strings. It's really just about amplification. So just 1 second here. All right, so acoustic guitars are just about amplification. And of course, the amplification idea is resonance, right? Like you have the vibration source. I think I have a bunch of steps in here, but we have a source frequency, and it gets pumps energy into the standing wave. It's really, the amplitude is getting bigger, the energy is building up, it's resonating. And all those same topics from before with resonance. So you can picture the 1/4 wavelength being longer if you have them all closed versus if you only have some of them closed. Okay, so then you have a 1/4 wavelength that fits in there, and that's for a longer wavelength, therefore a lower frequency. The bigger this number is, the smaller this number has to be, because of course the speed of the sound is always the same, right? So the longer the wavelength that fits in other words, the longer the air column, then the lower the frequency that resonates with it. So all sorts of instruments, you can picture the trombone is very obvious, has a very obvious length range for pitch or note or whatever selection. And so it's about the note and the amplification, pitch and amplification. And you can just be like, et cetera, et cetera. You can just picture all sorts of instruments. They have sometimes they have an air column. Usually they'll have an air column for amplification, and sometimes it's for picking out frequencies as well. So demonstrations to do with this. I didn't do a video of this one yet. I might have to just put a link to it later. So I have a computer subwoofer box, and just basically unscrew the speaker and take it out of that box, and it's a much quieter sound than when it's in the box, because that box is serving as an amplification. It's an acoustic resonance thing. Acoustic guitars, if you cover the sound hole, they get really quiet. And of course, electric guitars are quiet on their own, right, without the electric amplification. So the air chambers amplify sounds for sure. So for keeping track here again, we've got standing waves and mechanical waves, and we have it in sound waves as well. Plus, we already saw this in the other lesson as well, right? The flames and whatnot. But now we're itemizing out the exact wave pattern and using it to measure, wavelength of the sound and so on. Pretty surprisingly easy to do, right? Since you can't see sound, but you can actually still measure the wavelength fairly easily. This is just some fun stuff here, where people take this kind of thing to the next level here. So under the sea, yeah, under the sea. So again, if you're looking for physics in the world around you, you might you're looking for physics in the world around you, you might see a video on YouTube, or you might, like these guys did, do a little project while they're on vacation, I guess. Not bad, right? Very talented. What would they have to make the different sounds? They would just have the bottles filled to different depths, right? And so the wavelength that shows up or that resonates is the one you hear. Because apparently it's maybe the same people, I'm thinking. Getting some money from their physics knowledge. What else did I have here? Oh, the toy pig. My dog has one of these toy pigs that makes this sound, so I kind of laughed when I saw it. But again, it's just the same stuff. Pig. Very strange, I know. So a bunch of different air columns. And so when he's making a really low note, you'll see the pig oinking over top of the longer air column, and higher notes when it's over the shorter air column, for the exact reasons we just talked about. Come Dog would be going crazy. Be like, Piggy, where's Piggy? Running around the house looking for it. And then this guy here, same thing. This one's a lot harder to tell because it's like a maze of pipes, right? Rather than them just being like all a long length. But the overall effective length, and you see that in instruments like French horn and in the saxophone, the way it curves and whatnot. It's the overall path length from the start to the finish that really determines the resonance. So pipe guy. Surprised.
This is one of the most advanced rain jackets ever invented.
Link works with not too long of an ad. That's good. Very neat, right? But resonant lengths all being used for those things. So you've got questions. I reduced some of it here for you. So just parts of these, it's just kind of big looking. Overall, I think you'll find a lot of them fairly quick and easy. How does the length of a brass instrument affect its sound? Well, obviously, the longer the length, the lower the sound it's going to resonate with. Purpose of the body of a guitar or violin, we've already mentioned. The amplification, of course. Like these aren't long, drawn out questions, some of them. And then up here we have some calculation questions, like the stuff we did in the lesson. Okay, so hopefully that all makes sense to you. And yeah, thanks for watching.